All right, here we go. Problem number 4. Problem number 4. We're looking for SiH4. Silicon's in Roman 4, has 4 electrons. Hydrogen's in Roman 1. They have 1 electron. We've got 4 of them times 4. We've got a total of 8 electrons to work with here. Obviously, silicon will be in the middle. Silicon is the one that needs the most bonds. It needs 4. Hydrogen can only make 1 bond, so it really can never be in the middle of a molecule. So silicon will go in the middle, and we'll surround it with 8 and attach the hydrogens. So we have silicon surrounded by 8. Wherever there's a pair, we can attach a hydrogen. So we can put a hydrogen there. We can put one up here. We can put one over here. And we can put one down here. If you recall, we figured we had 8 electrons to work with on this molecule. We have 8 on the molecule. Silicon has the 8 it needs, satisfying the octet rule. Hydrogen has the pair it needs, satisfying the duet rule. So we don't need to erase any or add any electrons. We can just go on and finish off this molecule by replacing shared pairs with lines. So we have our molecule right here. Now it is time to determine its shape. We begin by counting the number of things on the central atom. We call that the steric number. Things would include atoms. We have 4 hydrogens on the central atom silicon, so we have 4. And then there are no lone pairs, which is our E. So we have a total of 4 things on the central atom. All atoms, no lone pairs. And we already know the shape of this thing, or the family shape. When there are 4 things surrounding the central atom, we see our 4 right here. That puts it in the tetrahedral family shape. So when you have 4 total things, it is in the tetrahedral family. If we take a look at our shape sheet, we are now in the tetrahedral family. So we have 3 more problems to do. If you've been following the pattern, we've just been kind of going straight down. First one we did was linear, then trigonal or trigonal planar, then we did an angular or bent. Now we're on tetrahedral. I'm guessing problem 5 is trigonal or trigonal pyramidal. Problem 6 is probably angular or bent. So we had 4 atoms, no lone pairs. So the actual shape is tetrahedral. It is the tetrahedral shape in the tetrahedral family. To confirm that once again, we have 4 bonded atoms. B is bonded atoms. We have 4 bonded atoms, all hydrogens. So we can put a 4 right here in this column. And there were no lone pairs. There were no lone pairs, so we can put a 0 in the lone pairs. So we are at a 4, 0. 4 for our B, 0 for our E. That is the tetrahedral molecule in the tetrahedral family. So we can circle tetrahedral. Now we come down. We've got a 4, 0. We've got the 4, 0. So we can finish off our shape formula, AB4E0. AB4E0 is the classic formula for the tetrahedral shape. You can just write AB4. You don't have to write the E0. And when we look at our shape sheet, we can see that the angles of the tetrahedral shape are 109.5. So we can write 109.5. There really aren't any axial or equatorial here because they are spread out evenly around in the space surrounding them. So there's really not an equator or an axle to the entire atom. So we go ahead and put our 109.5 right in there. Now we have no lone pairs. So we come through here and we have all the same type of atoms surrounding the silicon. So in this thing right here, we can circle same. Our E is 0, so when we pop out of here, we're going to be dropping down towards the E equals 0. If the atoms are the same, and they are, and our E, our lone pairs, we have none, it becomes symmetrical shape, so we can circle that. With that said, when it's symmetrically shaped and you have all the same kind of atoms on this thing, I'm telling you, it doesn't really matter what the bonds are, whether the bonds are polar or not. If the bonds were polar, the symmetrical shape would cancel them out. Doesn't really matter. If the bonds are nonpolar, the molecule is still going to be nonpolar. So we come from symmetrical We follow this right up here. We follow right up on the line. Symmetrical pops us right out. It is a nonpolar molecule. There's no sense in wasting time really determining the electronegativity differences. We know the strongest intermolecular force, IMF. There's no charge to this molecule, so it's not ionic. There's no dipole, so it's not a polar molecule. The strongest intermolecular force would be London dispersion forces. It's a nonpolar molecule. We are finished with number 4. SiH4s would not stick well together. They are very weak intermolecular attractions. And if we look on right here, it is a colorless, toxic gas. Well, we know now why it's a gas. They don't stick together. Let's take a look at number 5. This is a wild one, the hydronium ion. And this is our first one that actually has a charge to it. This is a positive charge, which means this molecule will have one less negative electron when we total the electrons up. There's one oxygen with 6. It's in Roman 6. There's 3 hydrogens in Roman 1. They each have 1. That's 3. 6 plus 3 electrons is 9 electrons. It is positively charged, which means there's 1 fewer negative things on there than we would suspect or expect. So we subtract off a negative thing. There should be 8 electrons to work with on this molecule. Who's going to be in the middle? Oxygen has 6. It needs 2 more to get 8. Hydrogen can't be in the middle. It can only make 1 bond to get 2. So we're going to put the oxygen in the middle and surround it with 8. As we added up just a few minutes ago, we were allowed 8 electrons. There they are. Wherever there's a pair, we can attach a hydrogen. So I can put a hydrogen right over here. I can attach a hydrogen on this side to this pair, and I could attach a hydrogen maybe to this pair right here on the bottom, and we have the hydronium ion. Remember, when there's an ion, we put brackets around it, and we write the charge outside as a superscript. That means there is 1 fewer electron on there than we would expect from what the atoms, each atom would bring to the molecule. Here we go. Electrons add up. Hydrogens have their 2, satisfying the duet rule. Oxygen has its 8, satisfying the octet rule. We can now replace shared pairs with lines. All right, it's time to take a look and figure out what this Lewis structure is, what type of molecule it is. We start off by counting the number of things surrounding the central atom. We have 3 hydrogen atoms, which count as 3, and 1 lone pair of electrons, which count as 1 thing. So 3 atoms and 1 lone pair. That is 4 things surrounding the central atom. Knowing that we now have 4 things surrounding the central atom, we can declare what type of molecule it is, or what type of family it belongs to. Anything with 4 things around the central atom, whether they're bonded atoms or lone pairs, that falls into the tetrahedral family. So it's in the tetrahedral family. Which member of the tetrahedral family is it? We can get that by realizing we had 3 atoms on the central atom, and we had 1 lone pair on the central atom. The 3-1 takes us to the molecule, which we call 3-1 is called trigonal or trigonal pyramidal. It has a pyramid shape, a 3-sided pyramid shape to it, because what happens on this molecule here is this lone pair will force those 3 atoms downward. It'll force those 3 atoms downward, and those hydrogens will actually make a 3-sided base, or 3 sides, which were 3 sides to the pyramid, with the lone pair being on top of the oxygen. A trigonal or trigonal pyramidal shape. Our shape formula then will be AB3E or AB3E1. They mean the same thing. What are the bond angles for the trigonal or trigonal pyramidal? Well, we remember when we had tetrahedral, the bond angles were 109.5. And that's when we had 4 atoms. But when one of the atoms is replaced with a lone pair, as we see here, that lone pair repels better. So the angle will push the atoms closer than 109.5. And if we look on your shape sheet, we'll see that it'll actually push them to a 107. Here's the 3 bonded atoms, 1 lone pair, trigonal or trigonal pyramidal. Angle is 107. We see it's asymmetrical on the shape sheet. So our angle is going to be 107. So we went ahead, we put in the 107 right here. Now let's take a look and see here. Do we have the same or different types of atoms surrounding the central atom? We have the same. They are all hydrogens. So we can circle same. And these atoms are not going to be evenly distributed. Our E is not equal to 0. Our E is equal to 1. Our B is not a 2. Our formula is not AB3E3 or AB2E3, and it's not AB4E2, so we don't go there. We're going to pop right up to here. E equals 0. That is asymmetrical. So if it has different atoms, and it doesn't, and E is not equal to 0, it's not, it's equal to 1, we have an asymmetrical shape. With the asymmetrical shape, this is how we can get a polar molecule. So if it's an asymmetrical shape, it can be a polar molecule, but it has to have polar bonds. So we need to come up and find out what the bonds are. We already know oxygen in anything is going to be polar. But we come back here and we look at the fact that this has a positive charge. It is an asymmetrical molecule, but it has a positive charge. So the fact that this molecule might have poles on it doesn't really matter. It will have poles on it. But the strongest thing on here isn't going to be the partial charge poles. The strongest thing on here is going to be the fact that it is fully charged. So when we come down to this bracket right here, we want to circle that the strongest thing this has is a full charge. It is ionic. Knowing it's ionic, would there have actually been dipoles on this molecule if it wasn't charged? Absolutely. Oxygen's 3,5, hydrogen's 2,1, difference is 1,4. That would be a strong dipole on there, but not as strong as the full charge. We'll finish up, and in our last video, our very last video, we'll be coming down to our final one on today's homework assignment. We'll be doing the amide ion, NH2 minus.